This is problem 15-23. Blocks A and B, which weigh 200 pounds and 120 pounds respectively, are connected by a rope as shown in the figure below. During motion of the bodies, A, determine the acceleration of block A and the tension in the rope connecting the bodies, and B, determine the acceleration of block A if block B is replaced with a constant force of 120 pounds as shown in the figure. Okay, take a second and think about the fact that there is a part A and a part B, and try to think why having a 120-pound block in the figure A would be different than having a 120-pound force on part B. Shouldn't be the same thing. Well, let's do the analysis and let's find out. So first, we're going to take each block. They have a mass, and we're going to make a free body diagram for each. So we'll have block A, and then we'll have block B. Now, these are two separate free body diagrams, right? But I'm going to focus on A first. So A has a weight of 200 pounds. Okay, and then there is a pulley. Let me go ahead and put that pulley there just for extra reference. And there are two ropes, and they are actually fully vertical. Don't mind my sloppy arrows. And they're going to have a tension. And since the tension of the pulley is going to be the same on both sides, we can label both tensions with the same label T. Now, if we go over to block B is going to have a weight of 120 pounds. And then there will be also a tension T. This is all the same rope. And the pulleys do not have any friction, and they don't have any rotational inertia. So the tensions are going to be equal for that one rope as it is passing through all the pulleys. All right, you will see in future classes that the pulleys will have mass and rotational inertia and friction, and the tensions will not be equal. Right? But in this case, with all of those things being neglected, the tensions across the ropes, the single rope through the pulleys will all be the same. All right, so where do we go with this? Well, we want to take the forces from the free body diagram and we want to put them into Newton's second law. So we were going to start, let's start with block A. We're going to have the sum of the forces of A equal to the mass of A times the acceleration of A. Okay, oh, in the y direction, that's what I mean to write. Okay, so what are the sum of the forces? Well, we're going to have the tension twice, so 2T, and then minus 200 pounds. Okay, and that's going to be equal to a mass of 200 pounds minus the acceleration due to gravity. Okay, so we're taking the weight and we're subtracting or dividing out the acceleration due to gravity to get the mass, right? And then that's going to give us the acceleration of block A. Right, and then we can also, I'm just going to come over here and do some of the forces of B is equal to the mass of B times the acceleration of B in the y direction. Okay, so we have one tension going up and then minus the 120 pounds going down equal to the weight of 120 divided by the acceleration due to gravity to get our mass, and then times the acceleration of B. All right, well, we can get our accelerations, but then we can't get our tensions because we have three unknowns. We have the tension, acceleration A, and acceleration B. We need a third equation. Well, where is that going to come from? We've already done our free body diagrams, and the block is only moving vertical, so we can't do some of the forces in the X or anything like that. So what we have to do is we are going to have to analyze the lengths, the dimensions of the rope. All right, so if the rope is going through the entire system, so we have the rope, we have our first pulley coming up, going through our second pulley, and then coming down, then we're going to have basically a height for block A. So the book likes to use S. And then we're also going to have the height of block B. So they're not exactly the same. I could exaggerate this a little bit, but they're not always going to be the same, actually, is more important. As these blocks move, the heights of A and B will change. A will go down while B goes up. So that means that these lengths later on could be like super long down here, with this one being really short. Okay, so B could be only this long and A could be much longer, right? So that's why we have to distinguish between the two lengths. Well, there is a full length of the rope. So as A goes down and B comes up, the rope doesn't change length. B comes up and gets shorter and allows more length for A to go down. So there's a total length, and we'll call that L. The total length is equal to 2 lengths for distance A plus 1 length for distance B. Because see what happens here? I'll use a different color. This is the distance of A, and then this other chunk here is the distance of B. So at first B would be long, and then when they're even, A is also the same length as B. But as A increases in length, the orange lines, then the green line gets shorter. So there will always be 2 lengths of A and 1 length of B. They can change, but they will always be that ratio, and the total length of the rope will always be the same. Therefore, L is a constant. Okay, so now if we want to learn something about accelerations, remember the whole goal is to get a third equation. And right now, there's no tension and no acceleration in this third equation. So this isn't necessarily helping us. In fact, we don't know any of these lengths. But what we can do is we can do a derivation as a function of time. So since L is a constant, we go to 0 equal to 2 S dot A plus S dot B. This is totally allowed. Okay, and then we do a second derivative. 0 again is 2s double dot A plus s double dot B. Well, what do I have now? Well, what I have is I turned a length into a velocity into an acceleration. Well, s double dot A is, if we consider the length of A to be up here is 0, and down here is the actual length value, and again 0 and the actual length value, then that means that our acceleration is going to be upward being the negative of the motion downward. Okay, so that might have been confusing, that we consider our accelerations up here to be positive in the up. This is an acceleration. In fact, it's an acceleration of A, technically, but we had biased our positives to be in the downward direction. So therefore, we are going to be equal to negative the acceleration of A. And then S double dot B is going to be equal to the negative acceleration of B. All right. So that allows us to have an equation that is 0 equal to negative 2 A sub A plus negative A sub B. This is our third equation. Okay, now we can do 3 equations, 3 unknowns. Well, if we do our substitutions and try the math out on your own, the acceleration of A is going to be equal to 1.894, that's supposed to be a 9, feet per second squared in the upward direction. The tension is going to be equal to 105.9 pounds. All right, that answers our ultimate question. For part A, now part B gets kicked into action, and there is no block B, there is just a force. So I'm just going to draw this next section in a different color. And let's redo this free body diagram equation, because now we're going to end up with, we don't even have a block B to make a free body diagram for. So that means the sum of the forces of A equation end up changing. And what that means is that we end up with a system. Let me make a little bit of room here. We end up with a system that is, we have our block A, we have our pulley, we have our rope, okay, and there's another pulley, and we just have a force. So since I can't draw a free body diagram, and there's just a force here of 120 pounds, well, that force is on the rope, and the rope is anchored to the ceiling through two pulleys. That means we actually do know this T value now, just automatically. It's 120 pounds. Okay, so our new equation is going to be 2 times 120 minus 200 equal to the 200 minus the acceleration due to gravity, acceleration A. We don't have a second unknown. We don't need a second equation. We can solve for the acceleration of A immediately. So the acceleration of A for part B is 6.44 feet per second squared in the upward direction. Because we get rid of that mass, we can't draw a second free body diagram. And also, since that mass got turned into a force as applied directly onto the rope, we now know the tension of the rope. Also, we'll learn more in the future of other dynamics classes about inertia and then the fact that an object's mass will actually affect acceleration in various different ways. And so you can't just treat a force that happens to be the same as an object's weight the same way as a weight that actually has that force. There are other factors that get in the way. And we can see here that we end up with two totally different answers for the acceleration by just swapping the box out with a force.